Well, here are my explanations. Let's start with the cereal because it seems the simplest, but it turns out to be one of the most surprising. The simple explanation goes like this. So I showed you cereal is magnetic. I have ground up all of this cereal into a very fine powder. Let us see what is in it. I'm going to take these strong magnets and run them over the cereal powder and see if anything is attracted to them. Look how the cereal actually sticks to the magnet. And it's because there's pieces of iron in this cereal. They've been added because iron is something we need. It's an essential nutrient that we need to survive. In fact, this cereal has 60% of your recommended daily intake of iron. But there's more to it. I received a video response from Martin Bear showing non-magnetic objects like plastic and paper also apparently being attracted to a magnet. So how does this work? Well, water is diamagnetic, which means in the presence of a magnetic field, it generates its own magnetic field in the opposite direction. This means the water is very slightly repelled by the magnet, and this causes a depression in the surface of the water into which a floating object will slide. You can even see this depression by looking at the reflections off the water. So cereal is attracted to a magnet due to its iron content, but when floating on the surface of water, there is an additional effect: the depression of the water's surface due to its diamagnetism. I showed you that you can find the center of mass of a cane or another stick-type object just by moving your fingers in towards the middle from the outside. But how does this work, even when you start in, say, an asymmetric position? Well, one finger is closer to the center of mass, and therefore it carries more of the weight of the cane. And so the friction force between your finger and the cane is greater until the point where the other finger catches up, at which point this finger slides in, and eventually they must meet in the middle. So this is a way you can find the center of mass of any cane or cane-like object. I showed you that if you try to flip your phone end over end, there is no way to do it without it also rotating around the short axis as well. Why is that? The phone has 3 axes about which it can rotate. There is the long axis, which has the maximum moment of inertia, meaning it requires the most torque to accelerate it in that direction. Spinning about the short axis has the least moment of inertia. Then there is the intermediate axis, which has a moment of inertia in between the other two. Now, the intermediate axis theorem says that if you try to flip any object along its intermediate axis, it will not maintain simply that rotation. It will also get rotations in any of the other directions. That is, if there is any slight deviation from a perfect rotation. So why does this happen? Well, the mathematics is kind of complicated, but it's similar to the mathematics of a rigid pendulum. So if you're flipping the phone along its long axis or its short axis, the phone acts a little bit like this pendulum in that any perturbation will cause it simply to go back to where it was before. But if you're flipping it along its intermediate axis, it's as though you're trying to balance the pendulum on its end, in which case it's very unstable, and any slight perturbation may cause it to exponentially increase. So that is why you can't just flip your phone along its intermediate axis without it also spinning along one of the other axes. I showed you that an electrically charged object can deflect a stream of water. But it is not due to the common explanation, the common reason which is given, which is that water is a polar molecule. So what really is causing this water to be attracted towards the cup? Well, it is charges, but it is ions. It is dissolved ions in the water. There will be some OH ions, some H+ ions, and there will also be some other impurity ions in the water. So what happens when you hold this negatively charged cup up against the water stream is it will repel the negative charges, the negative ions in the water, some of which will go back up into the tap. And that means the water coming down will be slightly positively charged. And once it breaks up into droplets, those droplets have a positive charge that they can't get rid of. So now those positive droplets are attracted to the negatively charged cup, and you can see those droplets swirling around the cup because they are so attracted to it. So this is not actually a very good demonstration of the polar nature of water. Even non-polar substances with some ions dissolved in them will deflect in exactly this way. So this is actually showing us that water droplets are charged. They are charged by induction, and it is not due to the polar nature of water that they are attracted to electrically charged objects. Now you know.
In the teabag rocket, we showed that if you light a teabag on fire from the top, it will actually take off into the air. That happens because as the teabag is burning, all the air inside it heats up, and so it expands, so it gets less dense, and it's pushed up by all the cooler air around it. You know, sometimes people talk about how hot air rises. I mean, that is what hot air does, but only because the cooler air around it is pushing it up. In essence, it's like a buoyant force because the hot air is now less dense than the cooler air around it. So when the teabag burns right down to the bottom, the remaining ash is so light that it gets swept up in that convection current, and you get a teabag rocket.
So do you agree with all of my explanations? And did you get them right the first time? Let me know in the comments.